Um, Hello everyone. Today I'm going to be talking about field flatness. So, the field flatness is an important figure of merit, and this is really specific to cavity design, as far as I know. So, this shows how uniformly the energy is distributed over the cells, and this is the formula. Although in literature you could see some other formulas, so it's given in percentage. So 90, maybe 95, 100% field flatness is just tells you that the peaks have the same value. If I could scroll this, so maybe you should look at the on axis field. So you have this peak, so this peak values, so the using this formula, so the maximum of the peak values, so EP means peak, so the maximum of the peak values electric field, and then minus the minimum, then divided by the average of the peak values, then 1 minus. So that's the field flatness. Although in some other literature you could see this formula which removes the 1. So for this, why you'd be getting your answer maybe 90, 99, 100% would be a perfect field flatness, but with this formula 0% would be the perfect field flatness. So to do this in CST, I mean, I don't really know if you can do this from templates, the typical template result post-processing. But one thing you could do is you could export the on-axis field to a file and then use maybe a code like Python to run it. But then there is another way, which is the use of VBA. So I went ahead and wrote this VBA script. Now I'm not an expert, so maybe there are more efficient ways of writing it, but then this is the one I could come up with. So, first things first, what should I do? Okay, so I'll just go over the code and explain. I'll go over the code and explain what it does. Maybe I could move this over here. Yes. Okay, I'll go over the code and explain what it does and then calculate the field flatness for the Tesla cavity. So, I'm getting ahead of myself there. So first thing, if you want to create a VBA to do this, you'd go to home and then macros, and then you go to let's open make VBA macro. Then it's a control macro. Then you could name it maybe field flatness calculation or something, and then leave it as control macro because it's going to control a process or get your result. Structure macro is to build models. So once you are done, you click OK, and then it would take you to, I've already created one, so I don't want to click on that again. So I already have evaluate field flatness. So now I'm going to go into edit. So I'm going to look for my evaluate field flatness in the edit the global macros and then edit it. But then if you if you created a new macro, then this would be empty. Or I think maybe you would have the sub main. So, but then I already have stuff in here, so I'm just going to leave it. And then you save the macro. There's a way to make it global. I think I'll figure that out later because if you should create the macro, then it would be okay. I think I'll just create one instead of talking, because there's a place you'd select to make it global, because the one I created is available to all my files. So I'll just go to, you could also import make VBA, and I'll just call it test delete because I'm going to delete it later. And then yeah, make globally available. There it was. So I don't need to create it, so I don't go and delete it. Okay, I'll just create it. So when you create it, this is what you have, and then you can start writing your code in here. So I'll leave this and then delete it later. So I'm going to close this, close out of this, and then go back to field flatness, which I opened for editing. Now this is your sub main. I don't know the technical name for it in VBA, but then yeah, you have functions too that I wrote to perform some specific tasks. So when we get there, I'll also move over to the function and explain what it does. So what we want to do is to access the results from this. So I already went ahead first of all to get, because we want the on axis field, so we want EZ on axis, and for that you go to post processing and then result templates. Okay, I don't think Tesla has it, so I'm going to create one. So 2D 3D result, then go to evaluate on arbitrary coordinates. Then this would be a 1D curve, and then I select Z direction and I want it to be on axis, so X and Y 0. Then I select the field result to no mode 9. Oh, it's actually 7 modes. So I think the 7 was the pi mode. I think, yeah, that should be the pi mode. Then I go to the magnitude, and I think that's that. So okay, and then I evaluate it. Yes, mode 7 was the pi mode. So you have this peak. So what we want to do basically with the VBA macro is to extract the peak values. Now you see it's not very smooth. So I think the mesh I used was really not refined. But then this is just for show. So we want to extract these peaks and then get the maximum of these peaks, also get the minimum, and then get the average of these peaks. So that's what we are going to be using the VBA macro for. And then this is kind of, you could also, I mean, for this I explain how to also access different results. So if you need to manipulate other results inside of CST, because one thing you could do, like I said, you could easily export this to an external, export the file and then load it from Python and then solve it. That's also okay. But then if you want something that you could always use CST, then you could access your results with what I'm going to explain here. So although it's specifically for field flatness, you could maybe get some idea on how to use different results and stuff with VBA. So I already have E absolute. Now going through this, I'll just call it method because I don't know what it's called in VBA. Going through this main method or main function, you have the you have the definitions of the variables. So dimensions, parts as variant. So I think your variant is kind of like an array. So your variant holds arrays. So the types and all of them are variants, because what the next line of code does, so result tree accesses your result tree, which is in your navigation tree. So you could access from your result tree, you could access your 1D results, 2D, 3D results, and also your tables. So for this, we want to get 3 results. And then so we want to get 3 results, maybe one of them or all of them. And then the results we want to get is located in tables. Under the tables, I think you could also just type yes. So result 3 object in the CST help. You could just search result 3 objects, and then you see the different methods and their their input arguments and then their outputs. So for this, it gives you the parts, the relative parts to the, no, the absolute, it gives the absolute parts to the results here, and then you could get the files from those parts and everything. So this gives the parts, gives the type of the results, also gives the file name and then some other information about it. So that's it. So it goes to tables, which is this, and then it looks for 0D and 1D results. So it also takes folders. You could also remove folders here, folders. So this is one of the arguments it takes. So this just tells it to also look into folders and return folders. So you have your 0D and 1D result, their folders. Then you have your 0D and 1D results. That's what we are looking for. And then recursively, so it goes inside. So if you had a subfolder in here, it would go inside of these subfolders and give whatsoever results you have. So what this does is to print the results, and I could print I guess I could print it just to show. So I already wrote a method. I don't know if there's a built-in function in VBA or CST VBA to do this, but then I wrote a function to print an array which just loops over the array and print displays it on this window. So I could just print one of them. So I could just print the parts and go to messages, and I just run the VBA. Okay, now it's going to calculate everything. So I think I could just cut this part out so it only, yes, I hope that works. Yes, so this is what you have. So if you look here, you see tables, which is the folder, then you see table 0D result, another folder. Then inside of table 0D result, you have Lorentz force. And then inside of, you have tables 1D results, then you also have these other results. So that's what this does. So I could Control Z and delete this. So that's what we have. Then you also have the file names. Now the file names gives you the file that, because when you have these results, they are saved somewhere, although it's not visible because I checked the result. If you should go to Tesla and then check the results, you do not see. Okay, maybe what I'll do is I'll print the file names and then show that to you. This is y, yes. So I'll print the file names. Yes, so this is the file names.rtl.rt040d, but then if you should check this folder, you do not see it. I don't know why, although I've tried to turn on my show hidden items, I still can't find it. So I don't know how it is saved or where it is saved, but then that's what you have. So so I'll just go back and yes, because I don't want to mess around with it. Now, so it gives you all of these files in here, right? Recursively loops through everything. Now, the next is we want to access E absolute Z because that's what we need for the computation of the field flatness. So to access any of the results, now we just want to access E absolute, but you could access any of the results once you get this. Now, to access the results, we loop over the results. We loop over the results from 0 to the length of the results. We loop over it, and then because m results, I think it should give the number. I think this should be an integer, returns the number of results you have here. So we are looping from m is equal to 0 to the final number, which would be -1 because we're starting from 0. And then now we check if E absolute Z is in the file name. So file names gives the all of the results, and then file name m of course corresponds to the index. So and then we have to change it to string. I think it's already string, so I don't think this c string, I think this should mean cast to string, but I might be wrong, I'm just guessing. C string, but this should convert it to string if it were an integer, but I don't think this is an integer, so I don't think this C string is important. But then this function checks if this string, this substring is in this string, is contained in this string. So I'm checking through file name. So this is file name. So it goes through this and then checks if it contains E absolute Z, and you see that only one satisfies it, which is this. So when that is true, then this function returns 1. So when it is greater than 0, then what should it do? Now you could uncomment this to print out the information about the parts. Okay, I think I should change this to M. Oh, I should change this to M. Yes, it should, because we are looking over M. So it would give you information about the parts. So it's just basically what I did initially, but then just formatted. So to get the results from the result tree, file names, or we get it from the file path, actually not the file names. I was kind of stuck for a while because I was trying to get the result from the file name, but then we actually get it from the path. So get the 1D result from the result tree. So I call this and then we would also need the ID. So ID is when you run your sweep, you have where's the result navigator? You have the run ID. So we would need that later. So we just have one run here, so we have just 0. But then we need the ID later, so I just I got it from here. So result tree dot get result IDs from tree item. So you get the result from the tree item using your parts. So parts M corresponds to the index, and then to get the result, and then I just also save the table part because I just need it later for I need it later for some other purposes, just housekeeping. So now I guess this is wrong then. Get one, oh, get result ID, not get one the result. So this is the get result ID. So now we need to create a result object. So in CST you have result objects. We need to create a result object to hold the array of field flatness for all the parameter runs. No, I think this is wrong. What was I thinking? Because this is supposed to, okay, yeah, it's correct, it's correct. We want to get the field flatness in case there are multiple IDs. Yes, okay, yeah, I missed that. We want to get the result in case there are multiple IDs. We need an array to hold all of them, and this is the result. This is the ID. This is the result array I created. Now for each, now this is where we get the result. Now for each RID, so for each result ID in the list of IDs we got, we want to get the result. So to get the result, you use result tree dot get result from tree item, and we get it from the table part. So the table one, the part which is parts M, and then we also need the ID to get the particular result. So that's how we get the result. Now to get the Y, because what we need is the, where is that? I'll close this. What we need is the electric field, which is on the y-axis. We could also get the values on the x-axis. So where is it? Oh boy, okay, I thought I deleted it. Okay, still there. So to get the um, electric field, to get the electric field array, so not the peaks, just the electric field array, we get from E absolute Z, we go O, which is the object that is holding the results, and then to get array Y. So we could also put get array X, and that gives us the frequencies. Now I create another array to hold the peaks. So first off, we've gotten the entire array of all the electric field values for all these for this not frequency distance, for these z's. Now what we need to do is to get the peaks. Now the peaks would be another array, because for this we have 9, for other ones we might have 1 or 2 depending on the number of cells. So, and also the mode. But then for the fundamental mode, we know that for 9 cells we'd have 9 peaks. So we want to get the peaks. So I initialize an array. Is it initialized? Defined, declared. I declared. Initialization is when you give it value. Yeah. I declared an array to hold this peak. So the peak list. Very boring name. Now I look through the array. So the array of E absolute Z, and then I check. I get each of them, and then I check if yi is greater than yi minus 1, and then if it's not, so it's like it goes from here front to back, and then when it gets to this, when it gets to the peak, then the condition is not satisfied because the next one is less than. So it's like when it's increasing, the condition is not satisfied, but then for the first part, when it tries to decrease, then the first condition is satisfied, and then it returns the first peak. Now but then you will see that if you only pass this condition, then when it comes here it would take the trough, but then we do not need the trough. So that's why there's a second condition, which is and yi is greater than yi plus 1. So then we get then we redimension the pick list. So I mean, I do not really know much of the lingo of the VBA, but I know that what this does is to expand the array. At least I know that one. To expand the array, to increase the size of the array. So this preserve redimension, preserve pick list 0, and then to upper bound. So u bound is upper bound. So it takes the current upper bound and adds one to it. Now it's only after redimensioning before we can save a new value to the list, or else if you do not put this line, then this is going to give a problem that it can't find the index. It's not big enough. So then we get the maximum, the upper bound, the length, so the length of the list currently, and then we set the index, and then we save whatever maximum we get, so the peaks, whatever peak value we get. So that's what this block of code does. It extracts the peaks. Now that we have the peaks, we can now go ahead to get the maximum and the minimum. We need variables to hold that. So we have that we initialize this initially to 0. So the first so this is initialized, max is initialized to the first peak, and then mean also is initialized to the first peak, and then the average is set to 0, and then the n, which we would need for the average, is the number, which is the size of the peak list array. Now we look for each v in peak list. So for each of these peaks, in peak list, we peak list, we check if any of them is greater than the first one that we initialized to, and then if it's greater than, then we set that as the maximum, and then if it's less than, we set it as the minimum. So that's what this block of code does. So for each v in peak list, then we of course find the average, which would be the current average plus v over n. So if v is greater than max, then set the new max to v, and then if v is less than mean, set the new max to mean. So that's what this line of code does. It gives us the maximum and the minimum, and also the average of the peaks. Now to calculate the field for flatness, we just apply this formula, which I showed, and I'll show again. So I just apply this formula. Now if you were following this formula, then you would make away with the 1. Where is the 1? Where is 1 1 1? Yes, you would just remove this, and then you have the other definition. Now remember, this is just for field flatness, but then you could see how you could manipulate results from here, and then use your own formula and apply it and write the VBA. Now this is to print the results to the message. So you use report information to window. So that's what it used to print the results here. You could also clear it, but then that's what it used, and then it saves the results to your 1D results, which we'll see in a minute. So this block of code, this line of code, just print it out to your message box. And this, remember, I created a results array which holds all the results for all the IDs that we run, because we are looping through the IDs. So the result ID we got initially is actually different. So it's not a digit, it's I think I could type it maybe. So it's something like this. So the result ID is something like this, 3D result, I think so, or something like that. Then 1D number 1, no, I think it's 3D, maybe 1D or something. Yeah, it's something like this. So it's not an integer, which is supposed to be. It's not an integer. So what I did instead, I wrote a function which would extract the ID from this. So it just takes the last part after the column, which would be a number, and then cast it to an integer. So that's what this does. So extract 1D, extract ID, not 1D, from text. So that's what this does. It goes through the input text and then checks out the last colon, and then takes the value from the last colon. Now just for housekeeping, I also wrote another one to extract text from path. So that's for the saving. I'll show you that one later. So that's what we have. So the result for each ID is appended to this as a kind of XY array. So this would be the x, and then this is the y. So the x is the ID, and then the y is field flatness. Now after that is done, we save the field flatness to the tables. Want the result? No, this is wrong. It doesn't save to tables. I don't know how to save it to tables yet, but then saving it to 1D results, it also works. So it's to 1D results, which is this. Now this is what I need the part from now, because sometimes you have E absolute Z, sometimes you have E absolute Z, then maybe bracket 1 for boot 1, and then or E absolute Z copy and stuff like that. So in order to differentiate between the E absolute Z's that we're calculating in field flatness for, that's why I put field flatness and then appended the path. So each of these names, E absolute Z whatever, to the end of the result, so you could tell apart. So that's it. And then if I should go ahead and I could run it from here, and then it calculates the field flatness out, clears this, but then I would save this. I hope I didn't make any change. And then I could close the macro editor, and then if I want to run this for any shape, I just go to home and then macros, and then evaluate field flatness, and you see, okay, this is wrong. I think I changed something. Because this is 0.933%. This is wrong. I'd have to have a look again, maybe for the mode, but then I'd have to have a look. But then this is typically what it prints out. And to access the results, you go to 1D results, and then you see your field flatness E absolute Z, which corresponds to this. Now, what did I change that made this? I knew because it was asking to save. Edit. What did I change? Oh, I hope I can figure it out. This is correct. That's odd. Yeah, it's supposed to be that's odd. I guess I'll try it again because I don't know what I changed. In this code, it works because I already use it to calculate for some other cavity. Or maybe I could just copy this from here instead. So I'll copy this because it's the same thing, and then I would save it. Yes. Oh, it's still giving the same result. So maybe it's from the field. Because for this, although this is I think it's a 2-cell cavity. So for this, I ran I ran a sweep just to test that it works for when you have sweep and then different IDs. So I ran a sweep for this and then got this, and then when you run the evaluate field flatness, I had this where is it? Okay, it's not here yet. Okay, I'll just run it again and see if it's yes. So this is what I have, and then yeah, it's correct for this. I wonder why it's not correct for a Tesla cavity, but then you see that it has for sweep value 1, 2, and 3. So sweep 1 is actually, I mean, the ID 1 is actually like the correct value for this 2-cell cavity that gives the desired frequency that we want. Wait, I could close this and then just show that you could run it from here too. So you go to mode, or delete this result first. Yes. And then go to home, macros, and evaluate field flatness. And yes, you have it here. And then if you should go to messages, you will see the results on messages. So yeah, that's it. So it works for this, but I don't know why it's not working for a Tesla cavity. Maybe I'll go and look at my EAZ again and make sure that everything is correct. So mode 7 is the This is the pi mode, but then why doesn't it work? I'll just pause and then try and figure out what went wrong, and yeah, I'll let you know, because I'm going to copy the code anyways and maybe put it on the comment section, so you could just copy it and paste and then get your results. So I'll be right back. Okay, now I found the problem by, yeah, if I should go to evaluate field flatness, I included, what did I put? So I just printed out the maximum, minimum, and average to see what the values are like, and then what you could see, where is it? I think I could clear this and then print it again. So what you see is that the minimum is 11, which is totally wrong. So it's the maximum is correct, but then the minimum is the minimum of the peak values is wrong. But um, it's not because of the formula, but then because of the E absolute Z. If we should observe the E absolute Z, we would expect that we only have these results here. But then if we should zoom in, then you have some kind of hump from the, yes, so you have a curve, which is inside the beam pipe. So I mean, one way to fix this would be to put a limit, but then I don't really think that works. So it's like adding to this condition that here that the electric field must be greater than maybe 1 e to power 3 or something, but I don't think that really solves it. That doesn't would not solve for all cases. So instead, what I'm going to do is you still have this on the right, which is the field from the beam pipe. So okay, I think it's just the left, so you have 11. Let's see, reset, so just confirm that this is correct. So maximum, no, it still has some elements. So in this window I go to maximum and then I see what is reported, 11.26. yeah. So for the EZ, instead of getting for the entire length of the cavity, I'm only going to evaluate for the cells. So I'm going to go ahead and modify my result template, E absolute Z, and then settings, and then I'll go to Z, and then what I want to do is I do not want the max range. I want to get from minus Tesla cavities 1, 2, 3, 4, 5, 6, 7, 8. So I'm going to get from the left hand side, which is going to be minus L, I think it's going to be 8 multiplied by L. Is it? I think it should be more. Yeah, 8. Wait, which is the center? This is 1, 2, 3, 4, 5, 6, 7, 8, 9. So one cavity should be at the center. So 1, 2, 3, 4, 5, 6, 7, 8. Yes. Minus 8L. Now I don't know which one is left or right again because they have different lengths. So I'm just going to put minus 9L to plus 9L. So you should get the rate, although I don't really think it makes any difference because the fields here are also like not it's decreasing. So I'm going to put that and okay, and then I'm going to evaluate this, and now I have this, which gives me the peaks, which is what I'm looking for. Now if I should go ahead and evaluate the field flatness with the code, I could, yeah, I'll just go from here. So I go to home, macros, evaluate field flatness. Yes, I have 97.66%. Yes, that's what I was looking for. So I'm going to delete the printing, the debugging printing again. I'm going to delete this and then save it. I'm going to clear this and run it again. I'm going to clear this and run it again. So evaluate field flatness. And oh, why is it still printing this? Oh, come on. Let me see. I think it's still opened here. Okay, it's no longer open here. Let's see. Go to edit. Oh boy. And evaluate field flatness. Yeah. I don't want to print more than I need. So I just wanted to print the field report. I think I'm going to delete this. Let's see. Messages. Clear. And run. Yes, it's still printing the maximum. But I don't want that. Where did I print the maximum? See this. I'll just instead of wasting time, I'll just go ahead and look. Okay, yeah, found it. I didn't select all of them apparently. Yes, so that's it. I just wanted to print the field flatness, and yeah, that's it. And then you can access your result here. So you could go to maximum, and then this is 97.66. I think I should now the Tesla paper. I don't know if they reported the field flatness. Let's see. Um, Tesla cavity superconducting cavity. Yeah, there will be PDF. Whew. And yeah, while that loads, yeah, that's it. I'll copy this code like this and put it in the comment or somewhere if I can copy it in comment, and then you could just directly copy it, create your VBA and paste it, and then you're good to go. So I just want to compare the values that they have on this paper. That's I can't remember if they reported it, that's why I didn't on it initially. So fluid flatness in percentage. No, they do not report. I could just search. Yes, the field flatness of fundamental movers, then it's only mentioned one place. So they only said they want to preserve it, but then they did not mention the exact value they got for the Tesla cavity. So yeah, using their dimensions in the paper I showed in my previous videos, you'd get this value, and then for multiple runs, so when you have a sweep, you could also evaluate the field flatness, and then you get this. Now remember very important that your EAZ should be just for the cells, otherwise you might sometimes, because this I got good results, which is 90 something percent, which is, oh, this is 220. No, what's this? I think I run this again, and then yes, so I got 99%, 90 something percent. So it's like the field flatness usually in this range. If you should have maybe 74%, then you could already see it in your field profile that okay, you have one lower than the other, but then something like this you'd be expecting 90 something percent field flatness. So that's it for this video, and yeah, till next time.